Here's another recurrence. T of n is 3 times T of n by 4 plus n square. Let's use the recursion tree method again to solve this problem. We start with T of n, an isolated node, and expand it into the next level by replacing T of n by the right hand side. So the right hand side here is 3 times T of n by 4 plus n square, which we diagrammatically depict as n square with 3 children, each child being T of n by 4. Then we can expand this tree to one more level. For that we need to know what the recurrence for T of n by 4 is. So replace n by n by 4 throughout, and you'll get T of n by 4 is 3 times T of n by 16 plus n by 4 square. So we can expand this tree to one more level by substituting in place of T of n by 4 this right hand side, again diagrammatically depicted as n by 4 square with 3 children, each child being T of n by 16. And that's going to apply to all the 3 nodes. Each of them will have 3 children, T of n by 16 each. So we can continue this process again until the recursion bottoms out. That is, we hit subproblems of size 1. So at the very end, our recursion tree will look like this. So we'll have n by 16 square because when we look at the recurrence for T of n by 16, we're going to have n by 16 square. And then the subproblems are going to be of size 1/4 of this. So that's going to be T of n by 64. So we'll have subproblems of size n by 64 at the next level. And so when we expand the next level, we'll have n by 64 square as the value of the costs. So let's say that the recursion bottoms out at a height of h. So let's mark the level numbers. The topmost level is level 0. These 3 nodes are at level 1. These nodes are at level 2. These nodes are at level 3. And the recursion bottoms out when we hit subproblems of size 1, whose costs are T of 1. And this is at height h. And in general, at level I, the size of our subproblem is going to be the cost of each node at level I is going to be n by 4 to the power I square. Right, when I is equal to 0, this is n square. When I is equal to 1, this is n by 4 square. When I is equal to 2, this is n by 16 square. When I is equal to 3, this is n by 64 square. In general, for a particular value of I, it's going to be n by 4 to the power I square. And the number of nodes at each level will be 1, 3, 3 square, 3 cube, and so on. 3 to the power I at level I, and 3 to the power h at level h. And that's again because we are dividing each problem into 3 subproblems. So when we create the next level, we are going to effectively create 3 times more the number of nodes as in the previous level. Now to evaluate the value of t of n, we need to calculate the level sums. For level 0, the level sum is just going to be n square because we have a single node with a cost of n square. At level 1, we are going to have 3 nodes with a cost of n by 4 square each. At the second level, we are going to have 3 square nodes with a cost of n by 16 squared each. At the third level, we are going to have 3 cube nodes with a cost of n by 64 square each. In general, at level I, we are going to have 3 to the power I nodes, each with a cost of n by 4 to the power I square. And at the very final level, we're going to have 3 to the power h nodes, each with a cost of t of 1. So to calculate t of n, we need to sum these level sums. T of n is going to be, writing the last level sum separately, 3 to the power h times t of 1 plus summation of 3 to the power I n by 4 to the power I squared, I varying from 0 to h minus 1. Now to calculate this, we need to express h, the height of the tree, in terms of n. And we can do that by noting that the size of the subproblem is reducing by a factor of 4 at every level. When we created level 1, the size of our subproblem was n by 4. When we created level 2, the size of the subproblems we got was n by 4 square. And when we create level I, the size of the subproblems we're going to have is n by 4 to the power I. So at height h, or at level h, the size of our subproblem is going to be n by 4 to the power h. And by definition, the height of the tree is the level at which the size of the subproblem reduces to 1. So equating n by 4 to the power h to 1, we get h as log of n base 4. So if we substitute this value of h into the expression for t of n, we get t of n is 3 to the power h, which is 3 to the power log of n base 4 times t of 1 plus summation of I varying from 0 to h minus 1, 3 to the power I. Well, we can take n square out of this summation. So we can take n square out, and we can group together 3 to the power I and 4 to the power I squared. So we can express this as 3 by 4 squared whole thing to the power I. Now this will be n to the power log of 3 to the base 4 times t of 1, is swapping n and 3 here, plus n squared times this series, which is again a geometric series with the first term as 1, second term as 3 by 16, third term as 3 by 16 squared, and so on. And we have a total of h terms. So this is a decreasing geometric series again. The first term here is 1. The common ratio is 3 by 16. So the common ratio is less than 1. And so we can write this summation as a times 1 minus r to the power k by 1 minus r. So a here is 1. R is 3 by 16, so we get 1 minus 3 by 16, the whole thing to the power k, which is the number of terms, and that's h, divided by 1 minus 3 by 16. Now, we could substitute log of n base 4 for this h here and try to solve for this. But again, we could use the alternative approach which we used in the second example we saw in an earlier video, where instead of trying to derive an exact expression for t of n and showing that this exact expression is theta of some function, we can try to sandwich the value of t of n between two constant multiples of some function. In this case, we can note that if this series had only one term, that term would have been 1. Right? So the value of this series must be at least greater than 1. And if this series had been of infinite length, if this had gone all the way up to infinity, then the value of this series would have been a by 1 minus r, which is much easier to compute than this. A here is just 1 and r is 3 by 16. So this would have been 16 minus 3 by 16, or the reciprocal of 13 by 16, which is 16 by 13. So we know that whatever be the exact value of this, it must lie between 1 and 16 by 13. Right? So t of n is greater than or equal to n to the power log of 3 base 4 times t of 1 plus n square, and it's less than or equal to n to the power log of 3 base 4 times t of 1 plus 16 by 13 n square. So if t of n is bounded from below by this expression, we can argue that it's going to be bounded from below by some constant multiple of n square. The coefficient of n square here is 1. Note that the highest power of n here is 2. This value, log of 3 base 4, is going to be less than 1 because log of 4 to the base 4 is equal to 1. So log of 3 base 4 is going to be some number less than 1. So really this is the dominant term, and this is the dominant term here. This is a lower order term, and that's evident because if you have a decreasing geometric series, we've already seen this general pattern where if we have a decreasing geometric series, the overall complexity of the series is going to be determined by the complexity of the first term. And this very last term, 3 to the power h times t of 1, can be approximately fitted into this series with just a variation of a constant factor, because the number of terms, this first part of the term is uniformly increasing throughout, and it's going to be 3 to the power h here, which is log of n to the power log of 4 base 3 as we've seen, and this t of 1 is going to be some constant. At the penultimate level, we're going to have n by 4 to the power h minus 1. At the penultimate level, this term is going to be n by 4 to the power h minus 1 squared, which is going to be another constant. Let's look at that. N by 4 to the power h minus 1 squared, where h is log of n base 4. This is going to be, square of this. So this is going to be 1/4 of n. Right, this 4 to the power minus 1 can be written as 1/4. And then we have 4 to the power log of n base 4, which is nothing but n. So if we square this, n square and n square are going to cancel out and we'll get 16. So when we look at these terms, n by 4 square, n by 16 square, n by 64 square, and so on, they are reducing, and at the penultimate level, the value of this is going to be 16. And you can see that it's reducing by a factor of 4. So it's becoming 1/4 and then the square of that. Right, so this was n square here. It became n square by 16. Then it became n square by 256 and so on. So it's reducing by a factor of 16 in every step. The first part of this term is increasing by a factor of 3 in every step. So the penultimate term is going to be 3 to the power h minus 1 times 16. 3 to the power h minus 1 is approximately, it really has the same asymptotic complexity as 3 to the power h, which is log of n to the power log of 4 base 3. So the complexity of the penultimate term is going to be equal to the complexity of the last term, and that's going to be n to the power log of 4 base 3, which is significantly less than the complexity of the first term. So this is a decreasing GP, and so it's the complexity of the first term which should determine the overall asymptotic complexity of T of n. So we can say that T of n is greater than or equal to this expression, which in turn will be greater than or equal to some constant times n square, where we can choose this constant c to be a number like half, because here the coefficient of the highest order term here is 1. So if we choose a coefficient less than 1, say half of n square, we can easily argue that half of n square will, that this expression will be greater than or equal to half of n square, because n square is greater than half of n square. So if we take this term here, we get half of n square needs to be greater than or equal to minus of this term when it's taken to the right hand side, and that's trivially true. Right? So if T of n is greater than or equal to n square plus something, then it must be greater than or equal to some fraction of n square. That's trivial. Similarly, if T of n is less than or equal to this expression, then it must be less than or equal to some constant times n square, where we choose this constant to be greater than 16 by 13. Let's say we choose this constant to be 2. We can argue that 2n square will be greater than or equal to this expression. I'll leave the details to you, but you can figure out that if we take 16 by 13 on this side, you're going to get some fraction of n square. And on the other side, you will have a lower order term. You're going to have a power of n that's less than 1. So any constant times n square is going to be greater than or equal to any other constant times n to the power some number that's less than 1. So we can argue that T of n is bounded from above by a constant multiple of n square, by 2n square, and it's bounded from below by half of n square. And thus T of n is in big omega of n square, and it's also in big O of n square, and so it's theta of n square. And again, we note that n square is also the asymptotic complexity of the very first term in this geometric series. The value of the common ratio was 3 by 16, which is less than 1, and so this was a decreasing geometric series, and so the first term of the geometric series is going to determine the overall complexity of T of n, which is theta of n square.